So apparently, when I minimized the camera here on my desktop, it stopped filming, and I didn't realize that. So I was talking for a few minutes, and it was not filming, unbeknownst to me. So I'm just going to pick it up from there. Okay, so let's try this again. So here I am in Desmos. I'm not going to minimize this time. I'm just going to move it out of the way. Okay, so what I'm going to do, uh, Desmos will recognize if I put in r equals 6 cosine, it'll recognize that as polar. But when I get to the theta, um, as far as I know, I have to just spell it out. So theta, and then it will know what I'm doing. And there's the graph right there. We got the circle out at 6, sweeps back around to the pole. These two locations where you see that arc going through at radius 4, I believe. Oh, maybe I'm mistaken. Where's the very top? Right? Is that's the very top right there, and that's the bottom? Yeah. Okay. We can switch over to an XY style, and we can see that a little more plainly to us probably. And yeah, that's 3, 3 up at the top, 3, -3 down there. Switch it back to polar style. Pretty sweet. Okay. All right. You recorded that time. There is a second half to this problem. Find the Cartesian equation. Well, we know it's a circle, so we could probably get the equation just based on the fact that we know what the equation of that circle is, but let's pretend like we don't. Okay, so it's kind of awkward here, but I'm gonna show you. Okay, we're gonna start with r equals 6 cos theta. This is all we know right here. Those are, the different correspondences of converting. And, we're not sure what's gonna come into play. Any one of these four could be helpful to convert this to x's and y's. Well, what are we gonna do? And I really don't, there's not one answer here for any given problem. You just have to start trying things out. So, for instance, I see r there. Hey, if it was r squared, I could replace r squared with x squared plus y squared. So, you might think, what if I square both sides? That's a possibility. But if I square the right side, that's not going to do much for me. I do see cosine theta, though, and here's cosine theta. If it was r cosine theta, I could replace that with x. Hey, maybe instead of squaring, I should multiply by r. Then I'll get the r squared, and I'll get 6r cosine theta. And it turns out that's the way we should go. Multiply both sides by r. And then, we can substitute x squared plus y squared, and that r cos theta all becomes x. Now, that's what happens in this situation. In a different situation, maybe you should square both sides. I don't know. I mean, you just got to play around with it. A lot of trial and error. Okay, well, all right. I guess you could argue we've got a Cartesian something, but that really doesn't look familiar, and it doesn't look like a circle. So here's what we can do. Subtract the 6x over to the left side, and then, dun dun dun, complete the square. And usually when you mention completing the square, people like tremble, usually algebra students, like, oh no. Calculus students are not all that much different. Okay, to complete the square, what should we do? We should add something inside the parentheses. It's a 9, right? Okay, half of 6 squared. So we'll go ahead and add 9 right there. If I add 9, I should add it to the other side to keep it all balanced, and then I will factor this, and here's going to be a recognizable form. That's my circle. X minus 3 quantity squared plus y squared equals 9. That has a radius of 3, and it's centered at 3, 0. We got it. Oh, yeah, circle width. Center 3, 0 and radius 3. Awesome. Awesome. I think that's all on this page. I've got something else. Oh, we're going to graph more things right now. Now these I bring back just to discuss them a little bit more. Earlier we graphed r equals 2. So we know what the graph of r equals 6 looks like. We can do that just based on its polar style, right? The graph of r equals 6 is right there. It's the radius of 6 for every angle. No matter what angle you are thinking of, the radius is always 6. So it's going to be just making that circle. It's in orbit, right? It's just kind of going around the pole. Now here's what's pretty cool. Here's kind of some deeper meaning. That's the dependent variable, right? That's like the equivalent of y equals 6 in Cartesian. Well, y equals 6 is a horizontal line. What's my note here? The equivalent to a horizontal line in Cartesian, in polar, a horizontal line looks like a circle. Why is that? Because horizontal line, you're thinking you're just moving along a straight path. Nothing is interfering. But when you talk about polar, it's really helpful to think of that as like a center of gravity. So if I was just to, be moving along a path, I'm actually rotating about my center of gravity. And if I just keep moving along in that straight path, eventually I'm going to get back around to where I started. That is awesome. That's way more realistic, honestly. If you just shoot off, you're just cruising around, shoot off the Earth, and you start going around, even if you leave the solar system, right, you're still moving around the center of our galaxy. And eventually, you're going to end up back where you began if you just keep moving in a straight line. Wow. Okay, there's another part to this question, though. We need to get the the Cartesian version. Okay, well, you could probably get the Cartesian version just based on the graph. It's another circle. This time the center is 0, 0, the radius is 6. But how might that work, if you're trying to convert it, like, with our different pieces? Here you do literally want to square both sides. Okay, r squared equals 36. Why? Because r squared can be replaced with x squared plus y squared. Hey, there's the same circle. X squared plus y squared equals 36. Center 0, radius of 6. Okay. Moving on. Part C. Again, we talked about this one already, but we want to go into a little bit more. Theta equals pi over 3. Okay, I forget what the number was earlier. It might have been 2 pi over 3. This is going to be a line coming straight up out of the pole at whatever angle that is. So no matter what the radius for every radius, you're going to move at an angle of pi over 3. So something like that. And remember to go in the negative direction as well. This is equivalent, and it probably seems weird to say it, but if we had x equals, right, that's the independent variable. This would be a vertical line. This is the equivalent to the vertical line. What? How is that a vertical line? Well, again, think of this, the pole, as like the center of gravity. If you leave the pole, right, you're like leaving the Earth, then you're moving perpendicular to the direction of gravity, which if you're talking about an XY plane, like if the ground is here, I think you get it, and you move vertically, well, then you're moving perpendicular to gravity. Well, same idea here. Now, you can do that in any direction, though. But so long as you keep moving, there's no curvature. So gravity is not affecting you. You're just going straight against gravity. The equivalent of the vertical line. Okay, that's pretty cool. That's pretty cool. Hey, how are we going to get the Cartesian equation? That's another story. That's another story. Well, I think there's only one option. We need to take the tangent of theta, which means we need the tangent of pi over 3, which means tangent theta is y over x, and we'll just figure out what tan pi over 3 is. Hey, it's a square root of 3. I guess you could argue that you're done right here, but this is going to look a lot more familiar if we solve for y. Multiply that x on over. Hey, isn't this just the line with slope pi over 3 going through the origin? Yeah, that's pretty sweet. I don't know. I kind of like it in the polar form. That's more appealing to me. That doesn't really speak to like the you're going against gravity. All right. So I want to end this video just by exploring some other graphs. Okay. We're not. You might be asked to graph. I want to focus on these first. In the homework, there's going to be several problems that just ask you to look at the graphs. Okay. I want you guys to do all the graphing of some of the more difficult things in Desmos. Okay, so these, turns out all of these are in the same family called rose curves. So I'm not going to put it up on my screen. If we were in class together, we could do it up on the big screen, and that'd be pretty cool. But I'm just going to have you guys go into Desmos yourself and graph these one at a time and just kind of think about them. So r equals the sine of 3 theta. There's a reason why we call it a rose curve. It's got this flower sort of a shape. Not really so much a rose. I think that's a misnomer. It's more like a daisy, in my opinion. But okay, look at the sine of 3 theta. How about 2 sine 5 theta? That sort of thing. You'll notice that sine 3 theta, there are 3 petals, we call them. Okay. 2 sine 5 theta, there are 5 petals, and they're now 2 units long at the maximum, where here the maximum petal length is 1. Now we've doubled it. All right. If you graph r equals sine 4 theta, I know I'm going faster than what I intend for you to do in Desmos, so go in there and look when you're done with this. Sine 4 theta, there's 8 petals. You would think there'd be 4. But the way that it lines up, it never ends up copying back over the same points from 0 to 2 pi. So here, the period is pi when we have an odd number, just the way that those points get plotted. But if it's even, the period is 2 pi. And so sine of 4 theta ends up having 8 petals, which is pretty cool. And then cosine, let's throw 1 cosine in there. R equals the cosine of 3 theta, really to compare the first and the last. So they look very similar. This one, they've been rotated a little bit. So where this one has a petal going straight up on the y-axis, you might say, this one has its like main petal out on the x-axis. Pretty interesting. Just in general, the rose curves look like this. R equals a sine b theta, or r equals a cos b theta. If b is odd, then there are exactly b petals because the period is pi. If b is even, then there are 2 times b petals because the period is 2 pi. The rose curves. All right, there's another family called the limacons. All right, these are pretty cool. The limacons look like this: a number plus some coefficient times either sine theta or cos theta. So here you got the general form: r equals a plus b sine theta, or I don't know if this fits on the screen, r equals a plus b cos theta. So take a look at these. Here's the simplest one, and you'll notice as you change that coefficient, you'll notice the difference in the limacon. So at first, it looks like kind of a flattened circle. One part is just sort of flattened out. Then if you throw that 2, then that changes a little bit, and it starts to part of it starts to double back inside of itself. I want to say if you make it 1/2, it starts to flatten more. So I could be mistaken. I don't have these memorized, as you can clearly see. And then finally, compare 1 plus sine theta and 1 plus cos theta, and it's just a rotation issue. Here, the period is always 2 pi. It always takes 2 pi to make it all the way back to where you started. Finally, I thought I would mention circles, and I just kind of threw this at the bottom of my page. We did graph one of these, right? R equals a sine theta, R equals a cos theta. So a circle is just when you throw a coefficient in front of either sine theta or cos theta, and that coefficient will dictate the diameter. Sine theta versus cosine theta. Cos theta, it's moved out along the x-axis. Sine theta, it's moving up along the y. They're always going through the origin. And okay, that's it. We're gonna see these sort of things really when we get into integrals, which is the next section. But we're gonna see rose curves, limacons, circles, and that sort of stuff over there. Okay, let's end this video here. Have fun exploring these. See you in the next one. We'll talk about derivatives.